So today what I'd like to teach you is circular acceleration. So last time we talked about some of the basics. This is where circular motion becomes very different from other types of motion. Okay, so the first question I'd like you to make sure you understand is, why is there acceleration when you go around the turn in your car? Because after all, we usually think of acceleration meaning speeding up or slowing down. But realize it's not just that. Acceleration is any time you change velocity. And since velocity depends upon both speed and direction, even a change in direction will be classified as an acceleration. Not only is it classified as an acceleration, but it feels like an acceleration. Okay, so let's take a look at why. So imagine me in my car. I'm heading toward the building in front of us, which is Williamstown High School, and I have a Rubbermaid container wedged between the seats, along with a ball inside the Rubbermaid container. As I move toward that building, everything in my car is moving in that direction. And according to Newton, things that are in motion want to stay in motion in a straight line at a constant speed. So that when I turn my car, the ball appears to go to the passenger side of the car. But in reality, the ball continued to go straight, and it's the car that accelerated, the car which changed direction. Okay, so the ball was moving like that, and then as the car turned, the ball tried to go straight. So when the ball gets pushed by the box, it's going to force it to change direction. And that's what we call our acceleration. There are two factors that affect how much acceleration we feel. So let's imagine being in the car again. And let's think about the two things that are going to intensify the experience we have as we go around the turn. Hopefully you realize that those two factors are the radius of the turn and the speed at which the car is traveling. Okay? And it turns out that the faster we're going, the more intense the acceleration we experience. We tested that in lab, and hopefully it makes sense. When you go around the turn really slowly, you might not even feel it. When you go around the turn fast, your body is thrown around inside the car. In terms of radius, the smaller the radius, the more intense the experience when you go around that turn. If the circle is big enough, you may not even realize you're going around the circle because you're changing direction so gradually. In a small circle, you must change direction more quickly. Okay, so like I said, we tested this in lab. We had our little car. We had a little pocket lab inside to measure acceleration. We had the car moving on a straightaway at a constant speed, and then as it entered into the turn, we monitored the acceleration. You can see it went from no acceleration to about 1.5 meters per second of acceleration. And again, that is not caused by an increase in speed. The speedometer stayed in the same spot the whole time. That acceleration was caused by a change in direction. Okay? So that is the acceleration experienced by that car. Let's boost the speed to a little more than double the original speed and go around the turn again. You can see that the acceleration didn't double to 3, but quadrupled to around 6 meters per second. This shows us faster speeds give more acceleration, but it's a squared relationship, meaning doubling the speed gives 4 times the acceleration. It's 4 times more intense going around the circle when you double that speed. It's also 4 times more dangerous going around the turn when you double the speed. So as we saw before, you got to be careful with your speeds, because most of these things, the danger goes up tremendously with small changes in speed. Oftentimes when we're trying to describe the experience of an acceleration, we go with a term called number of G's. And the way number of G's works is it compares your acceleration to the acceleration due to gravity on Earth. You don't put the negative in there, that's just the direction. So you take the acceleration and divide by 9.8. If your number of G's came out to be 1, that means you're going with an acceleration of 9.8. If your number of G's is equal to 2, it means you're at 19.6. To get our number of G's, we take our acceleration and we divide by 9.8 and we get around 0.6, okay, about 0.61. Most times in a car, you're going to experience an number of G's less than 1. On an amusement ride, you might experience 2 or 3 G, maybe even more. That's why you go to the amusement park, to experience large number of G's in a safe environment. Okay, this former student of mine has a little thing inside his car, his race car, which will tell him the number of G's. And you'll notice there are 2 separate numbers. This red one is the one we want to focus on. That's going to be the turning G's. This one in blue is for forward or backward G's. So for instance, if he was sitting at rest and then real quickly hit the gas pedal and sped up, we would see this little ball, just like his head, move to the back, and it would tell you the number of G's up here. If on the other hand he's going forward and he jams on the brakes, that also will appear here, okay? This bottom number is for when he turns. And you can see here, the ball moves to the left, so that means he was turning to the right. Again, the ball is showing what would happen to his head as he bobs around inside the car. You can see this is a very large number of G's for a person to experience in a car. So with that in mind, if you watch him riding around some of these turns, you'll see how the ball moves left and right as he goes around turns. You'll see it move forward and backwards as he speeds up or slows down. And again, you'll see the numbers, and the numbers we're focusing on are the bottom ones. That's for the number of G's experienced in the turn. How do you find the number of G's in a turn? Well, first you start with your acceleration formula, which we haven't yet learned. This is for circular acceleration. This is not for speeding up or slowing down. This is for changing direction. You take the speed of the car, which happens to be 30 meters per second. You square it, and you divide by the radius of the turn, which in this case is 80 meters. Realize the radius of the turn would be if you completed this circle that the car is going in, how big of a circle would that be? And in this case, it would have a radius of 80 meters. So go ahead and plug in your numbers and get your acceleration. Once you get your acceleration, you then want to plug that in to our number of G's formula to find out how many G's the person is experiencing. Okay? And I had this person go pretty fast around this turn, so expect a pretty healthy number of G's when you work this out. On the other hand, when the Earth goes around the sun, even though we're moving really fast around the sun, the number of G's is going to come out rather small. One of the reasons why people did not want to believe that the Earth was in motion is because we can't feel the motion of the Earth. And the reason is we don't feel velocities, we feel accelerations. If we're moving at a really high speed but we're not changing direction or speed, we don't notice it. But when you change speed or direction, you can sense it. And the thing is, even though we're going to be traveling very fast around the sun, the acceleration is going to be really small. So let's test it out. What you're going to do is start with the formula velocity equals distance over time. I'm going to use S for distance because it's the arc length of this arc, which happens to be a circle. Since it's going in a complete circle, you can just use circumference. And for radius, use the distance from the sun to the earth. It should be like 1.4 something e to the 11th meters. Look up the exact value on your reference sheet. Okay, that goes in for radius. And for time, you're going to use 1 year. Don't leave it in years, but convert it to seconds. You will get the speed of the earth around the sun, and it's going to be a pretty big number. You're then going to square that speed and divide by the radius of the circle. And the radius of the circle, again, is the number you get off your reference sheet for Earth to Sun distance. That acceleration is going to be rather small. And when you find your number of G's, you're going to see that it comes out incredibly small. So even though the Earth is going to have a very high speed, it's going to have a very low number of G's, which means that we don't feel it. Okay, we don't feel that motion, even though it's very fast. I hope you realize it's because of the fact that it's a big circle that we're barely changing direction at all. 360 degrees in about 365 days means we only change direction by about 1 degree per day. All right, so a very small acceleration, a very small physical sensation.